need a detailed report in language that I can understand.
I will let you know.
That's 3 syllables or less.
I will let you know.
You know?
Hey, all right, so it's week 3, and so we're in, so this is NRGY 235, CTSN 283, and so what John Freer and I decided last fall is that the almost all the concepts that you're covering in green building design are things that we cover in NRGY 235, and so we figured rather than duplicate our efforts, we'd put the 2 classes together, and so thanks everybody for coming. Who's, is it carpentry? So 4 carpentry, and then who's energy? 5, okay. And Gary's somewhere in the gym, that's okay. So guys, what I want to do today, and I'll start off, pretty basic, pretty fundamental, and then just take just a few fundamental laws of physics, and then apply them to building energy efficiency, or green carpentry, if you will. So first thing I want to do is, I'm not sure if this is something that fully gets covered in your curricula. I just want to see where everybody is in terms of the relationship between power and energy. So anybody from carpentry want to just take a shot and tell me the difference between power and energy?
What I went through in chapter 1, a lot of the concepts we covered in green building until the end of the chapter, when we started talking about electricity and things like that, we didn't talk about that stuff.
Okay. So let me give you power and energy from 2 or 3 different perspectives. And in a lot of times, and I see this all the time. You read in the newspaper, and the reporters really will get the 2 confused, power versus energy. And it's something that, I insist that all my energy technology students, know the difference between. So I'll show it to you mathematically and then hopefully graphically a little bit as well. So let's just start out with power. Excuse my handwriting, I'll try to make it large, versus energy. First of all, give me some units of energy. Let's just start there. Okay. We've got joules. Meters per second, that's velocity. Right. Give me another energy unit. I heard kilowatts, and that's gonna lead us right down here. So power. The kilowatt is a unit of power. What's a similar unit of energy? Kilowatt hour. Yeah, perfect. Okay, and this is a very common distinction that has to we'll clear up. So kilowatt. See if I can't fix that W a little bit better. Kilowatts power. Kilowatt hours energy. Give me another. Well, just throw something out there. Another unit of energy you might have heard of. Say again? Calories. Keep going.
Kilocalories.
Kilocalorie, okay. That switches with a big C versus a little. It's 1,000 calories, sure. One thing you're going to see a lot of in building energy efficiency is the therm.
BTU.
Yep, you're going to see the BTU. You're going to see a thing called a quad. You might even see something called a ton. Believe it or not, there's a unit of energy called a ton. It's the
Which
amount
one
of
is that?
it's the amount of energy required to melt a ton of ice.
Would you spell it for me, please, sir?
Ton.
T-O-N?
Yeah. Which is kind of weird, because now you're like, oh no, I think ton is weight or mass or something. There's also a unit of energy called a ton. Okay, how about other units of power?
The watt.
Yep, kilowatt, watt, megawatt with a big M. What's the, those are all SI units or international units. What's the American Standard Power Unit that you talk about your truck in? Just horsepower, right? Okay. Now, how do we, is that,
I said Tor.
oh, I think tor's pressure. T-O-R-R, yeah, tor's pressure. Okay, so how do we get between energy and power? Because this is going to make a huge difference, or allow us to understand our power bills. What's the relationship between energy and power? Because first of all, they're different. They've got different units, and now we have to just understand, in what way they're different, but how they're related. Yeah. So a couple different ways to write this, and I'll just write E for energy. I'm going to write P for power, and I'm going to write lowercase t for time. So, going back up here, this first page actually is going to give us a little bit of a clue. Look at that kilowatt hour for energy and the kilowatt for power. What am I going to multiply by what to get energy or power? Okay, what am I going to multiply time by to get
Power times time.
Power times time is energy. Is that what you're going with? Okay. That's exactly right. So let's just do that little example. So energy just equals power times time. So for example, let's just do one super simple home energy analysis. Anybody know about how much power it takes to run the average American home? And this will kind of help us think about the difference between energy and power as well. 10 kilowatts. 10 kilowatts. Is it in your book anywhere? Yeah.
What it might be, I just don't know what Not necessarily, it's not it.
Yeah, it's not something you think about that frequently, because you go and look at your power bill, and it's billing you in kilowatt hours. But it's not like you're out there, looking to see how many watts are flowing through your system necessarily. On average, I'm just going to say average U.S. household is about 1 kilowatt. Is that more or less than a horsepower? Anybody remember how many watts in a horsepower? Let's do a little bit of conversion while we're at it. 1 kilowatt, bigger. So
I think it's less than 1,000.
So the question is, like, if it's
750.
yeah. So horsepower is about 750 watts, and believe it or not, if you just had 1 1/4 horses, you could run the electricity in your house. Kind of sounds small,
Yeah.
but it's true. The first time I looked at that, I'm like, wait, really? So it takes less energy to run my house than my car? And it's in a lot of ways it's true. We haven't looked at the heating components yet, but just in terms of electrical load, yeah, you could hook your car up to your house, stick a generator, and with the proper conversion, run your house off the electricity coming out of your car. And we're starting to see more of that with electric cars coming online. So we've got 1 kilowatt. That's the power to run a house. Now let's just do one quick, simple little energy bill. How many hours in a day? 24. So I'm going to take energy, again, equals power times time. So I've got 1 kilowatt. I'm going to multiply that by 24 hours. And what do I get? Well,
24.
yeah. Now, here's the deal with this thing. This is going to look super simple. You can see it. You can do it in your head. There's actually 3 components to every problem like this that you'll ever encounter. The first component is just the number. So 1 is a number. 24 is a number. I'm just going to call that the first component, which is a number. This guy right here, that's just the power of 10, and we know that kilo is 3, 10 to the third, so that's the second component. I'll put it, whoops, I'll put it 2 by that, powers of 3. And then the third component is, of course, the unit. That's the third one. So anytime you're solving some kind of building energy efficiency problem, the same thing's true in carpentry, right? If you're gonna be converting from inches to feet, you're gonna want to know how many of each. Usually you're never gonna say, kilofeet or milli-inches or whatnot. But if you're dealing with SI units, you're always solving these 3 problems at once. So I'm going to keep track of each one, and I'm just going to write that out as 24, because 1 times 24 is 24. So that's part 1 is done. The kilo on this little chunk does not have a correspond. I didn't say, mega hours or milli hours or giga hours or anything like that. So there's just kind of nothing there. It's just the kilo times nothing. So the kilo comes along by itself. The watt comes along as well, and then the hour. So there we just went from multiplying power times time to get energy, and the units all worked out. Okay. Let me show this to you one, and then of course you can go in and say, well, electricity in Montana costs about $0.10 a kilowatt hour. I'm looking at $2.40 for my power bill today, right? Add that up over the year or month, year, and you pay your bill that way. Okay. Now, I'm going to show it to you one more way. And this is something I think a lot of people, the numbers are fine, but I think a lot of us sort of think in pictures. So what I'm going to do is write it like this. And this is just sort of a different way to add something up. It's actually called integration. So if you've seen any calculus or done any calculus, you know what I'm talking about. If you haven't, it doesn't matter. You can sort of do this as a picture. So let's just say this is midnight. This is noon, and this is midnight again, the next day. So in general, the power. Actually, I'm going to rewrite this just a little bit here. I'm going to hold off on energy and power are both plotted on this curve. I'm just going to hold off on that for one quick sec. So you can leave it there or not. I just want to surprise you with the answer. Okay, so at midnight, what's running? Well, maybe maybe nothing's running for a while, or maybe you've got the laptop plugged in, it's sucking a little bit. Maybe your cordless drill is plugged in the garage, it's pulling a little bit, night light, whatever, but it's pretty low range.
Any question? If you get your cordless drill plugged in and it's not being used, that still pulls electricity?
Yes.
A little bit. There's an LED on there.
Even your cord plugged into the wall still pulls electricity without nothing to it.
Yeah, it's just called a phantom load. It's not much, but yeah, there's electrons sitting in that outlet ready to come out anytime you want them. If there's something plugged in, they're gonna flow through it. As long as if there's some little resistor in there, they'll flow through it. Not much, but yeah. So that's why I drew the line kind of low here. Now, yeah, someone said my fridge might come on. So there's this for a few minutes. Let's just say here's 6 a.m. So that your fridge might be doing this all night. And then all of a sudden you wake up, the lights come on, the fridge door gets open, the garage door opens up. I forgot to run the laundry last night, so you might have a little peek. Now you're out of the house, and it's, I don't know, maybe somebody's home, but the load is less. There's a few lights on. Okay, turn the lights off, et cetera, et cetera. You go through the day, the fridge is still doing its thing, and then you come home. It's 6 p.m. again. TV goes on, fridge comes open, et cetera, and then finally you go to bed. So, what's this curve that I've just drawn? Is that line itself a power curve or an energy curve? So the line itself is the power curve. The stuff underneath it is the energy.
Yeah, usage.
So we just did a little calculus, we just did a little bit of integration. So, I guess what I can do here, let's just do it this way. So I'm gonna label this in black as power, and then what I'm also gonna do is just say all this stuff underneath here. I'm just gonna try to shade this in. If you got a different color, that's great. If not, you can just make a note of it or make it dashed. All this stuff under here is energy. Well, where's the time involved? Well,
Times the left or right.
yeah, the time is just all these little chunks. So really, all we've done, getting from midnight to midnight, is in each case multiplied power. There's power right there by some little delta t, some little chunk in time, and all we did is add up all those little rectangles. So again, to reiterate, that black curve at the top represents power. All of the area underneath it represents energy. So obviously, the higher the power, the higher the load on the house, more stuff plugged in, I don't know, maybe it's the hot tub there later at night, you'd have a big spike. So you just add up all those little rectangles, like I just did, and that's your energy bill. Make sense? Okay. If we were putting solar panels on our house, what might that power curve look like? Where's it going to be?
Would go up initially and then slowly fall back down.
Well, after the panels are on and the sun is shining, where's that curve going to be?
The curve's gonna be high towards the mid part of the day. Low towards midnight on both sides.
It's probably gonna go below the line.
Yeah. So if you jack enough PV on your house, you're down here. Your supply is greater than your demand. All the stuff above that curve is your demand. If you put enough PV on your house, I mean, you still have the demand, but you could actually zero that thing out, and that's what's called net metering.
You're looking for the curve on the same line.
Yeah. I'm just saying, if you get, so anyway, so that's the electrical part of it. All right, so I just wanted to clear the air a little bit on the relationship between energy and power, because what John's asked me to talk a little bit about today is physics and heat transfer. And let me see how I'm doing on time. Yeah, I'm going to take a quick little break here. I'm going to basically give 6 20 or 25-minute chunks of this lecture. So hopefully that was a little bit of an icebreaker. We know the difference between energy, time, and power, how they're related, and how it relates to an electricity bill. So now I'm going to dig back down and dig a little bit into some of the physics that are important here. Okay, so quick break while I put this YouTube in the bank, and I'll be right back. Any questions at all on that stuff? Okay, so we know the difference between a kilowatt and a kilowatt hour, energy, power. We'll dig into that a little bit more in a second, but quick break.